Okay, welcome to the track 1 Maple in Education, the first session. And we have 4 little mini sessions for you, each of 10 minutes, which are supposed to be 7 minutes of presentation and 3 minutes for questions. But really people can adjust that boundary the way they like. I'd like them to adjust for more questions, but let's see how it goes. Our first speaker is Pilar Velez of the University of Madrid.
Thank you, Rob. This contribution is a very personal reflection of on some connection that we, Tomás Recio and me, has established concerning the unexpected links between the origin of computer algebra and the region of Canada where both Waterloo, the Maple's headquarters, and Niagara Falls are. Okay, we propose a travel in 5 stations from the origins of computer algebra to Niagara Falls through some intermediate stations concerning them. The first station, the origins of computer algebra, is in the decade of the 80s. It is reasonable to focus these origins in this decade to fix the concept of computer algebra. Most people in the scientific community will agree that the series of international conference ICSAC are the most relevant concerning computer algebra and symbolic computation. Indeed, there are precedents such as the SINSAN and some similar meetings in Europe in the 16th and 17th. But it's quite relevant to point out that during the SINSAN 1986 in Waterloo, here again close to Niagara Falls, it was the site unified under the name ISAC, the European and the American variant of these meetings. Let me add also that in this decade started the Journal of Symbolic Computation as well as many popular computer algebra systems as Maple or relevant documents that show the starting point of computer algebra research topics. In this framework, the 1982 collective book by Budberger, Collins, and Loss is, in our opinion, an essential document that presents for the first time a global panorama of the question addressed in computer algebra. In the introduction of this book, Loss presents a definition. For Loss, modern algebra is almost equivalent to computer algebra. Some years later, this ample conception becomes slightly qualified in the CIAN report. In its pages, we find that the role of algebra is clarified and symbolic computation is practically taken as a synonym of computer algebra. In fact, there is and there has always been a sort of dichotomy, the broader symbolic approach versus the more restricted algebraic one. The relevant role of these definitions in our story brings us to the next station in this travel, their connection to the aims of the well-known father of the computer, Charles Babbage. In the first half of the 19th century, he has to do with the so-called Analytical Engine, considered the antecedent of computers. Now, let us point out that it has not been disseminated sufficiently that for Babbage, the machine has to do with computer algebra in 2 senses. The first one on the possibility of computing with symbol with algebraic notation letter as declared by him in the text you can see in the screen. Remark the relevant role of algebraic computation in his declaration. It is clearly an imaginary father of computer algebra. But there is a second contribution of Babbage to computer algebra that had not caught enough attention to the experts. His interest is building a language to describe machines that gives an automatic way to construct these machines that performs certain tasks. It is indeed a true computer algebra approach, as the science to work with algebraic algorithms. This goal is connected to a very relevant scientifically and industrially problem that was a challenge for many scientists along the 19th century, to build and design linkages-based machine that would perform exactly some algebraic formula. And we are arrived to the next station, the algebraic linkages. All this work around the algebraic linkages started at the end of the 18th century with the arrival of the Industrial Revolution and arrived to a sort of end with the finding of the general method by Kempe to draw plane curves. But his proof have some errors. Note that at this moment we are limited to polynomials in two variables. But the full solution to this problem did not arrive to 2000 with the proof of Thurston conjecture by Kapovich and Milson, generalizing the Kempe's work to smooth compact manifolds. It shows in particular that linkages geometry is as complicated as possible since it has to deal with whatever geometric objects. It is our turn now to move to the fourth station, starting talking about máquinas algebraicas en español, algebraic machines in English, and Torres Quevedo. Torres Quevedo was an Spanish engineer. He published a paper in 1900 on computing machines, was the title, in the Concourse de l'Académie des Sciences de Paris. Having as referees Dupré, Poincaré, and Appel, declaring, this referring declaring. In summary, Mr. Torres has given a general and complete theoretical solution to the problem of construction of algebraic and transcendental relation by machine. He has, moreover, effectively by machine with a convenient handling. A more general solution appears here, related also not to produce the output, but to present an algorithm for constructing the machine that produces the output, as Babbage was looking for, but also with symbols, transcendental functions, not only algebra. Pure symbolic computation for us. Here you can see the scheme from Torres Quevedo discourse in the Spanish Real Academy, the scheme of this algebraic machine. And the right is a machine, is one of the devices he built to solve algebraic equations. We can say that Torres Quevedo was, in many respects, someone who accomplished at the beginning of the 20th century many of the goals by Kempe, Babbage, etc., and extended it concerning computer algebra and symbolic computation. Of course, the way he approached the solution, as in the case of linkages, was analog, not electronic nor digital. So we can say that our two, computer algebra, Babbage, algebraic machine, Torres Quevedo, are getting to the end. And we are arriving to the last station of this travel, Niagara Falls. The role of Niagara Falls in our story has to do with the so-called Spanish Aerocart, designed by the engineer Torres Quevedo. It has been operative since 1916, more than 100 of years ago. The Spanish
1 minute left. 1 minute left, including time for questions.
Okay, you can see the Aerocart from Niagara Falls. Then in summary, we hope we have shown you some interesting connection between two apparently far away objects. Next time you visit Niagara Falls, think of computer algebra and of Maple, of course. Thank you.
Thank you very much, Pilar. And we do have time for a question. If there are any questions type them into the Q&A part. And if nobody does, I have one question. So the history is fascinating for me, but you don't mention Don Ramon Lull. He was Catalan. and he had a computer algebra, an analog symbolic computing machine already several hundred years before. Did you know about him?
Yes. This is a very good point to include in the word, but we don't include it.
Okay. Thank you very much, Pilar. And,
advice.
okay, I will do that. Now we turn the talk over to Jürgen Gerhard. Jürgen.
Thank you very much, and welcome to the Maple Conference. And I am not going to present you a summary of my recorded talk, but instead I'm going to show you a few things which I skipped in my recorded talk. One of them is about visualization. So one of the things that we updated with the most recent version of Maple 2021 is the way arrows are being plotted. So this looks much nicer than it used to look in earlier versions. So this is an example of a vector sum plot from the Student in the Algebra package. And here is a custom plot showing a bunch of arrows in a spiral in different colors. The next gem I want to show, I have to scroll down here, is about performance improvements. And what I want to mention here is the speed of some kernel commands, such as map and seek, were improved drastically for certain frequently used operations. So on the left here, you can see what the operations are that were being measured. And on the right, you can see what the speedups are and the improvements also in memory reduction. And this is for a list with 2 million elements. And here is something similar. Again, the map command for a list of a nested list in this case of 1 million pairs of elements. And the main cause for the speed up is that garbage collection was reduced and improved. Next thing I want to show you is about image and signal processing. So there's a large number of new commands in the signal processing package, and there is a number of improved commands. And the one I want to present to you now is called music. So music, of course, is a cleverly chosen acronym. It stands for multiple signal classifier method. And I don't know exactly what that is, but I can show you an example why it is useful. So we start out by creating a noisy signal. And I have no idea why this doesn't show up properly. I guess maybe I forgot to execute a with command. Yes. Here we go. Let's try this again. Okay. So this is the pure signal which we designed, and then we added a little bit of noise to it. That's what you can see on the right. So you can visually see that they're a little bit different. And what we do now, we use the standard way of analyzing those signals, which is called a periodogram. A periodogram shows you what the contributions of the different frequencies in the signal are. And here it looks like the pure signal has a frequency at about 10 hertz, and then a strong contribution from a frequency at about 20 hertz. And from the noisy signal, you can clearly see the noise, but the most dominant peaks are still the same at around 10 hertz and around 20 hertz. But actually, the way we created the signal, there's 3 frequencies that are contributing, and 2 of them are very, very close together. So this is a very, very numerically unstable situation. And the music algorithm behind the music command is able to figure that out. And you can see that even for the undisturbed signal, the standard periodogram was not able to figure this out. I want to show one more thing about approximate polynomial algebra. So what I showed in the recorded talk is I talked about factoring and the Rupert matrix. So here I want to talk about approximate greatest common divisors. So this is a new package in Maple 2021 for approximate polynomial algebra. Maple could already do approximate polynomial algebra before, but mainly for univariate polynomials. And this package now can handle multivariate polynomials. So here's an example in 2 variables. We create a polynomial with floating point coefficients so that we get round-off errors and noise. And we multiply it, this same polynomial by 2 different polynomials. So the designated GCD is the original polynomial here, but already in the multiplication here, by expanding these, we introduced round-off errors. And now we look at the multivariate Sylvester matrix of f and g of order 3. So you can get one for every value here between 0 and the degree of the smaller of the 2 polynomials, I guess. And one property of the Sylvester matrix means, of this Sylvester matrix means, it tells us what the degree, what the likely degree of the designated greatest common divisor is. So on the left-hand side, we see the number of columns, which is 12. And on the right-hand side, we see the rank of this matrix. So this matrix has full rank. And since we computed the Sylvester matrix of order 3 here, this means that the rank, that the greatest common divisor has degree less than 3. And doing this for 2 and 1 and so on, or computing the rank for the original Sylvester matrix will tell us exactly what the likely degree of the greatest common divisor is. So this is new with this package. A lot of other approximate polynomial algebra packages, they require you to guess what the degree of the GCD is, and this package is able to figure it out on its own. So here we compute the GCD using the GCD command from the approximate polynomial algebra package, after we added even more noise. So we added some very, very small coefficients to it. And so we can see that the GCD already has the right degree. It has degree 2, but it does not look at all like the polynomial that we started out with. But if you look closer, you see that there's a lot of very, very small spurious coefficients. So we use the command fnormal to get rid of the small spurious coefficients. And then we also normalize the trailing coefficient, not the leading coefficient, but the trailing coefficient. And then it already looks very, very much like the designated GCD that we started out with to construct this example. And here we compute the relative error, and it's on the order of what the value of digits is. So for higher values of digits, this can be made more precise. Okay, and one last thing I want to show here is about language and programming. So we now have multi-level conditional next and break statements in Maple. So here's an example. I can say I want to break the second, not the innermost loop, which is a standard break, but I can break the loop before that and execute that. And then you can see here, there's a print statement which we inserted that this operation, the innermost iteration is stopped, but the next one is continued, and that actually triggers a continuation of the outermost loop as well. And we have something similar for next as well. And then you can even use a nice syntax here to have a conditional break and a conditional next. And I'll stop here and open the floor for questions. Thank you.
Nicely done, Jürgen. Okay, we have 2 questions in the Q&A. First one is, map and seek share similar capabilities. For a new user, do you recommend one over the other? Is there any significant speed difference when performance is required? That's between map and seek.
Yeah, so I'll answer the speed difference first. There should not be any speed difference really. And they're both very, very fast because they're implemented in the kernel. And the recommendation is use map or seek whenever you can over a hand-coded loop, because the hand-coded loops are executed in Maple, while these loops that are implicit in map and seek are executed in the kernel. Whether you want map or seek really depends on your application. If you already have a data structure, a list or an array or whatever, and you just want to transform each element in that data structure to something else, then you want to use map. If you don't have a data structure yet, but you want to build one, and according to a recipe for which is the same for all the elements of that data structure, then you want to use seek.
Okay, I'm going to skip some questions. There are some we can answer later, and ask a question from Saha. I just start to learn Maple. I am a CFD researcher. Can we do mesh or grid generation in different physical models such as 2D, 3D cavity using Maple? Also, can we solve system of nonlinear equations n by n when n is very high? So
again, I'll choose to start with the second part. The answer is yes. So first of all, Maple is both a symbolic and a numerical computation system. And systems of nonlinear equations can be, nonlinear equations, sorry, I misread linear equations. So systems of nonlinear equations are very hard to solve in general, either numerically or symbolically, but Maple can do both.
Okay, thank you. I'm going to cut you off now. Michael and Scott, we will answer your questions offline, and John will answer your questions offline if we can. And now we'll move on to Zoltán. So Jürgen, if you would stop sharing, please. Thank you. And thank you very much. Zoltán.
So good morning, good afternoon. Can you see my screen? Can you hear my voice? Very good. So this is joint work with two colleagues with Rafael Lozada and Thomas Recio. Thomas is here in the audience. And well, it's actually a story about 3 tools and 4 methods, and about their usage in so say a classroom environment, but of course not just in high school, secondary school, but also at university or at research. So the topic is about a geometric inequality that was studied very deeply, among other inequalities, by Bothama and his colleagues in the 60s. And we used, first of all, GeoGebra, because it is a classroom tool, a free tool. And we managed to prove actually this inequality, but not the equality part. So GeoGebra is a free tool available for many users. And we learned that there are some problems, even if GeoGebra has a built-in technology now to use real quantifier elimination and cylindrical algebraic decomposition. I think Matthew England is here in the audience, and maybe not just he, but other people were yesterday at a wonderful tutorial. Rob, you were there, given by Professor Maza. And it was actually about some very similar that Maple can do that also by using the regular chains package. We will use Maple in this context, not for proving the inequality, but just focusing on the equality part and to finish the story, because the other 3 methods will be also quite helpful. So what is it about? This problem is in a planar triangle. The sum of the sides is always less or equal to 3 times square root of r, where r is the circumradius, and equality holds if and only if these 3 sides are equal to each other. So this was the GeoGebra part, and GeoGebra in the background, behind the scenes, sketches up couple of equations, inequalities, and finally it learns by using external system. It is called Tarski, and it used the QuepCat-B system. So it learns that this inequality holds, but it cannot do anything with the equality part, even if we have a nice output here. So the second option to learn something more about the equality is to use the command locus equation. Locus equation, implicit locus equation means that we are searching for the point C here in this context, where to put C in order to, for example, A plus B plus C equals to R. So this is the question, and we can learn, okay, if I put C on this curve, then I can get this equality. But of course, we are interested not in this equality, but here the right-hand side should be 3 times square root of 3 times R. And in this case, we don't get anything. So no plot is produced, just because the number of points are just a couple. So 4 points should be there, but GeoGebra cannot plot these 4 points either. On the other hand, we can obtain this nice polynomial in 2 variables, and we will be able to manipulate further this polynomial either in Maple or in a different way in GeoGebra by using, for example, dynamic coloring. The dynamic coloring means that we put some values, different values, to the whole complex plane, actually, or a bounding box of the complex plane in the polynomial. And then if we have white points here, then we can have a picture on what the zeros are of this polynomial. So we have a conjecture, okay, maybe 4 points exist for zeros. And if we use Maple, and now Maple has an important role in the story, then we learn that it is also very important which package is used for plotting the algebraic curves. So the second one is algebraic curves. The command plot real curve gives a much better output. And if we use the same idea for this big 16-degree polynomial, then we learn, so at least graphically we have these 4 points. And in this case, we can learn, these 4 points, at least 2 of them will be associated to the regular triangle case, and 2 others are degenerate cases. So finally, we had to do some more sophisticated computations, not the regular chains method, but a so-called slow method, but can be understood by students as well. So by collecting the coefficients in X, finding the discriminant, and learning the number of real roots using Sturm sequences. So this is how Maple put together the whole story. And finally, we managed to learn that the equality case will hold only in at these 4 points. So that's the long story in a short form, and we acknowledge the joint work from Carlos Bueno, who had us a bit too. Thank you so much.
Thank you, Zoltán. Okay, we have 2 questions. The first one from Saha is, how do you obtain the polynomial p of x and y? You had that lovely polynomial there. How do you find it?
Well, we have maybe I show you the Maple file. So these are the equations here, and these are set automatically by GeoGebra. We need to do that manually in Maple. But if we have them, then we do an elimination, so a polynomial and ideal elimination. And then, so this is the, well, no, not here. I think, yes. So this elimination ideal command delivers. Mm-hmm.
Thank you. And the second one is just a comment from me, actually. Thank you very much for saying that plot real curve in the Algebra package does the one you want. I wrote that code 20 years ago. So
really?
Yes.
Okay.
Thank you for that.
Great,
and
great.
It needs some work, but there we go. So are there any other questions? No? Okay, then thank you very much, Zoltán. And
thank you so much.
We will switch now to Robert Lopez. So, Robert.
Okay, I need to share my screen.
Please.
That. Okay. All right. So I'm looking at the linear system differential equations. A is a constant matrix, so x prime equals ax, and A is defective. So there are not enough eigenvectors. Typically, in a textbook, what's taught is a naive approach. You start with the eigenvector that you have. You obtain a generalized eigenvector by solving this equation. This is the generalized eigenvector you're looking for. This is the eigenvector you have. That gives you a solution of this form, and you go up the chain, starting from the eigenvector up the chain by continuing to solve an equation of that form, and these are the corresponding solutions. Is that enough? Do we do our students a favor when we teach them that? So here's an example. For 4, lambda is repeated 4 times. You have one eigenvector. You can generate these 3 generalized eigenvectors by going up the chain. It worked. So there's an example where the naive approach works. Now here's an example, 3 by 3, repeated eigenvalue 1. You have 2 eigenvectors. You need 1 generalized eigenvector. So you try that trick of going up the chain based on V1, and you get inconsistent equations. It doesn't work. You try it with V2, inconsistent equations. It doesn't work. You need a specific linear combination. You need a specific eigendirection in that eigenspace in order to go up the chain. So you begin to see that the naive approach may have some difficulties. Here's an example, 4 by 4. You have, again, 2 eigenvectors. You try to up the chain trick. Going up the chain from either V or W, it fails. You find a linear combination, so there's a specific eigendirection that you can go up the chain 1 step, but then you can't get that remaining generalized eigenvector. So really, you need to invoke some Jordan form theory. So I call that Jordan's ghost hovering in the background. Is it going to spook the situation or not? What's key here in this Jordan theory is you look at the null spaces of the matrices A minus lambda I raised to the power K. Those null spaces become supersets one of the next. They're proper. And you need to go to the end of the chain. You need to go to the top of the chain and select a vector in that top null space that's not in the null spaces below. Given that vector, you just multiply by C to come down the chain. So coming down the chain is consistent with knowing something about Jordan form theory. All right, let's see. Can I do this here? All right, I'm stuck here. There are 2 things that help characteristic polynomial in the minimal polynomial. Minimal polynomial, the power here is 3, tells you that the chain here is going to have length 3. So we have, in this example, number 3, the null spaces. This is the first one. This is the next one. This is the whole space. So you need a vector in this space, which is R4, that's not in here. And the best recipe that I can come up with for finding that is to form a projection matrix that projects down onto this null space and take the orthogonal complement. If you do that, so you got the projection matrix and the subtraction, that gives you the vector in this space that's not in this space, and then simply by multiplication, you get the generalized eigenvectors going down the chain. It's a much simpler approach, and given a tool like Maple, the calculations are reasonable. You're not doing a tremendous amount of arithmetic. And here, the proof that I've got the appropriate set of generalized eigenvectors is if you put the vectors into a matrix, K, it becomes a transition matrix that takes A to drawdown form. You've got the right vectors, you can write down the solution to the differential equation. Okay, you can ask me questions.
Thank you, Robert. I have two questions of my own, and there's one in the audience. Let's begin with the question from the audience, which is for us non-mathematicians, and to motivate students who study this problem. Could you provide us with an example of a physical real-world system for which the matrix would be defective?
No, it can't, because if you read the worksheet that actually, the bigger worksheet that this was extracted from, I have a comment from a colleague, an engineering colleague at Rose-Hulman, who claimed that there are no defective matrices in the real world, because in the engineering world, the numbers in the linear system, so they end up in the matrix, they come from capacitors, resistances, which are not known exactly. They're floating point numbers. You never are going to get a defective matrix in the real world. So part of what I'm suggesting in the actual long presentation is why don't we look at our curriculum more carefully and do a better job of deciding what we should be teaching our students and what doesn't need to be in there. And the comment that I have is, when calculators became available, slide rules disappeared. When computer algebra became available, what's disappeared? I don't think anything has disappeared.
So to follow up on that exact point in two different ways. Well, one is, why don't you use the matrix exponential command? All of this algebra just disappears when you've done in your talk, when you just take the matrix exponential.
Well, that's exactly the point. Okay, this is what's in the textbook. This is what instructors expect to find in the book that they purchase from the publisher. Is this really the optimal stuff to be teaching students? I leave that to, I mean, I'm 80 years old. I'm out of the game, right?
No, you're very much in the game, my friend.
You guys are still in the
game,
right? You're the ones that have to decide, is this the right stuff to be teaching our students?
I'm retired too, but you are very much still in the game. And so the matrix exponential is something you would prefer over these manipulations that you've done here. Okay, I get that. And now I strongly disagree with you on your point where you say that defective matrices don't exist in real life. When you consider bifurcation phenomena, when you consider differential algebraic equations where the constraints are known very, very much to high accuracy, it turns out that you do get defective matrices and multiple eigenvalues and multiple complex eigenvalues as the parameter moves through the regime where these things do happen. So it genuinely does happen in engineering applications, that resonances really matter and all of those sorts of things. So we could take that discussion offline, but no, I think that we do need those things, and I can provide examples.
Let me just remind you that all I was doing was reporting a comment by an engineer colleague. I was not agreeing or disagreeing.
Okay, but you could have disagreed with them. But anyway, that's fine. We're not at the stage of throwing chairs at in this show. But anyway, let's see if there are more questions for you. So, but yes, seem to be well. And comment from the audience. Nice talk. Lagrangian dynamics. On the last example, why computer projection matrix rather than just considering the null space of the transpose of the matrix of vectors in the basis for the null space of C squared?
I don't know. I've never thought of that. I'm going to have to look at that and understand just exactly what that gives me.
Yeah. Okay.
I mean, the examples I look at in textbooks, they use easy numbers because they have no way of computing, so everything is simple. And they typically the authors say, this works. We can try this. It works. But they don't give you a recipe for figuring out how to do that. I devised this scheme because in Maple, it's easy to do. Projection matrix, subtraction, you got it. Now,
Yeah.
if there's a better way, great. I will look at that and learn something. But at the moment,
Well, I
it
would
appears
type
to be new to me.
I would type matrix exponential and avoid it all, but that's beside the point. Anyway, thank you very much, Robert. And do we have, I don't think I see any more questions specifically for you, but we have a few more minutes left in our session, and we missed some questions for some of the earlier speakers. So if some of the earlier speakers are willing to answer, I've got one question for Jürgen. You also went through the changes to arrows quickly. What specifically changed to make them look more arrow-like?
I saw that question and I decided not to answer it because I don't actually know.
Okay. And Mike asked, why didn't the approximate GCD automatically normalize?
I don't know either, but I suggest to ask the developer, Jean-May.
Okay, that's a good question. So that one is done. I didn't mark it done earlier. Are there any plans to improve symbolic statistics, such as conditional statements? That's for Jürgen as well.
That would probably be a question for Eric, but he's not on the panel.
He's actually here.
I'm actually not directly involved with Maple development anymore. I'm just doing the demo.
Okay. I'll ask Eric to answer that question later if he's not able to answer it now. It's probably not actually in the session, even though he's logged in. Okay. So the Saz asked, can we calculate the exponential of a defective matrix? And I believe the answer is yes. And I'm tempted to bring this stuff up, but and try it live on camera. But maybe Jürgen, if you've got Maple handy and a matrix exponential, are you willing to try? Oh no, because we'd have to think of a defective matrix, and we don't have enough time to do that. The answer is, I believe we can do it.
Yes, you can. All of these examples, you can get the matrix exponential. But I would remind everyone of the paper 25 years ago or more. I think it was 1979.
19 dubious ways to compute the matrix exponential.
And then 25 years later, they came back. They updated it by an addendum where they took into account more of the ability of computer algebra systems. So,
and if you know the data exactly, the answer is yes, you can do it. Right. The way George Lebon's code does it is interpolation, and so yeah, it does a very nice job. Okay. One more question. I am new to Maple as well. I am teaching linear algebra and would like to try this in my class. Do students find easy to do programming in Maple? There's somebody that's a question for Robert.
I like point and click mathematics because in the days when I was in the classroom teaching with Maple, there was only commands, and I had to teach students commands in order to get them to do stuff in Maple. And there was pushback. The pushback was, hey, I came to learn calculus. I didn't come to learn the computer language. So I like the point and click. I tend not to do stuff where students would have to do programming. Okay, I like the ability of point and click Maple to circumvent the need for knowing syntax of commands, and you can think conceptually about what it is you're trying to do. You're trying to solve, you're trying to integrate, you're trying to differentiate, and you're assembling those bits, and you're not worried about the order of command structure. So that's my preference.
Okay, thank you. That's a good answer based on experience. And also, as Scott Gould has posted to everybody, see Scott's talk in the pre-recorded sessions, what sells and what doesn't, and do the answers. So I think I'm going to close it at now and thank all the speakers and thank all the participants for coming. And let's go have our nice little coffee break and eat our cookies and come back for the next session. Okay, thank you very much. Bye for now.